All right, now let us work on question B. I didn't say in the last video that this was question A, but yeah, so last video was question A. How much work is done by friction? So now let's focus on question B. So for that one, let's use blue. B, how much work is done by the rope on the sled in this distance? Same distance, right? 30 meters. So the given, I'm going to copy it because we need a lot of space. Where did it go? Oh, here. And we'll change it to blue. And I'll say this is question B. Is it uppercase? No, lowercase. Question B. This was question A. Should have said that. And we need to find the work done by the rope, right? And work done by the rope, so the force that is present in the rope is tension force. That's right. So we say work done by the rope. What it means is work done by tension. Because we know tension is a force. Okay, so we don't need to find the work done by force or friction. We need to find the work done by tension. So work done by uppercase T. And we don't have an equation for tension. I'm just going to leave this here. It's not hurting. Okay. And we can use the same equation, right? So we know what before. Now let me just write down the equation. So work done by tension would be the force of tension, T, times the same distance, 30 meters, times the cosine of theta. Okay? And I'm going to copy, well, I'm not even going to copy. I'm just going to use this as a guide. So the force of tension is this one, right? And we use the force of tension when we sum the forces along the x direction. So I am going to copy this one. Okay, I just copied this one. Nothing crazy. Because this one will help me see how to find the work done by the force of tension, right? Because we don't have the force of tension. They just say tension was 100 newtons. No, it's just, I mean, there's nothing about tension other than the fact that is shown in the picture. However, I can make this equation be equal to better said, I can rearrange this equation so I can define tension in terms of mgx and force of friction. So then what I do is I take the equation only without the summation of forces. So mgx minus tension plus friction equals 0 because we're going at a constant speed. Oh, wait. I did a plus. Your signs, they can make you or break you. Okay. So you can move the force of friction, you can move mgx, or you can just add tension to both sides. This cancels, and now my equation reads tension is equal to mgx minus friction. Do we know what friction is? The force of friction? Yes, here. Do we know what mgx is? Yes, it's over here, right? We solved for it. So now we can say tension is equal to mgx, which is mg sine alpha, minus force of friction, which is this one, coefficient of friction, mg cosine alpha. Okay? If you don't remember how I got this equation, this formula, watch the previous video. I'm not gonna say there's a link in the description because I don't know how to do that. Okay, maybe you guys can teach me how to add the link or something. So now I'm pretty sure you guys can see we can factor out mg, right? Because repeat it. So let's factor out mg for fun. Tension equals mg times the sine of alpha, right? Mg sine alpha minus mu cosine alpha. There you go. That is an equation for tension force. Now before I substitute, what is theta? Well, theta is in relation to the force of tension. The force of tension has the same direction as friction, which is opposite to the motion. And we said that the direction of motion follows this one, right? So the angle between direction of motion, which is this one, it matches mgx, right? I can even move it again. I can move it here. So the angle between this point and this one, force of tension, is 180 degrees, half the circle. Okay? We said that force of friction was the same. It was against the motion. They're maximizing the work negatively. So then theta is equal to 180 degrees. So that means the work done by tension is equal to tension times the distance times the cosine of 180 degrees. This is -1, so then work done by tension equals tension times distance times -1, which is simply negative tension times distance. Now, guys, this makes sense because we said that negative work was present when we had a force acting against the motion. This one became blue. So tension and friction are acting against the motion, against the direction of motion. That's why they're both negative, right? So now we can substitute this equation here. So the work done by tension is negative mg sine alpha minus coefficient of friction times cosine alpha times distance. We want to keep the letters together, so we have the work done by tension equals negative mg d times sine alpha minus mu cosine alpha. Now we have everything we need, right? And I'm sure you guys can see how important it is to draw the free body diagram whenever you have forces, even though we're using the definition of work, okay? And we have the mass, we have acceleration due to gravity, although I didn't write it down. I forgot, but everyone, well, not everyone, right? But you guys know it is 9.8 meters per second squared. We have distance, 30 meters, alpha, 60 degrees, and mu, 0.1. Substitute, or like the math teachers like to say, plug it in, and you're going to get the work done. And this is question B.